Okay, so we're back, and now we're going to draw the representative volume element at principal stresses. So just, when we drew this first point here at A, this first point here, this point didn't necessarily represent the whole representative volume element. Rather, it represented the face perpendicular to x equals, to x, or theta equals 0 degrees. So this right here on this face, we had 1 ksi in tension and -3 or 3 ksi in shear going this way, this face, Okay, it represented this face. All right. Now, what we want to know is, this is 3 ksi right here. This is 3 ksi shear stress, okay? 1 ksi here. Now what we want to know is, what does this face look like? Okay, this face looks like. And in order for me to go from A to my major principal stress, I need to rotate an angle right here. I'll call this alpha, okay? That angle alpha is just the inverse tangent. So alpha is tan inverse 1 of opposite over the adjacent, 3 over 1.5, and that is 63.4 degrees. And in order to get to this to go from A to sigma 1, I have to rotate clockwise. So clockwise, or like this, right here. A rotation of whatever angle in Mohr's circle is half in the representative volume element. So here, or what I call real life, okay? But on the representative volume element, I go half what I go in Mohr's circle. So theta P1, the principal stress 1, the angle to there is alpha divided by 2, which is 31.7 degrees clockwise, or this way right here. And what that means, if I go now over here, is in order to draw, because I'm always referencing from 0 here, theta equals 0 degrees, I need to go 31.7 degrees in real life. So what I do to draw my representative volume element is I always start with the horizontal line first. That represents theta equals 0. It's my reference. And then I say, okay, I have to rotate 31.7 degrees. So then I draw the line at 31.7 degrees. So here, bam, right here, and this would be 31.7 degrees. Okay, that's 31.7 degrees. I don't know if you can see that. Oh, I just lost everything. Okay, so here, again, one more time. Whoa, one more time. Bam, right here. And then I have some angle that's representing 31.7 degrees right here. So this is 31.7 degrees. 31.7 degrees. And then now to draw my representative volume element, I draw a line perpendicular to this 31.7 degree line. So I draw, bam, like this, and then I complete the square right here. This I find is the best way to draw my representative volume element without getting confused. Okay, so I have this right here. And when I go to this point right here, this point right here, the sigma 1 represents this face here. Okay, so the state of stress at this point represents this face. And there is, I have 0 shear stress, and I have a normal stress of sigma 1 equal to 2.85. And because it's positive, or that means it's causing tension, so I'm going to have here 2.85 KSI. And then over here on the opposite side, I have equal and opposite 2.85 KSI. Now, I could also go over here. I have this, I could, I have a bunch of choices, okay? I could either rotate to get to the minor principal stress. I could rotate, this way. I could rotate this direction right here. I call this beta. And I know that beta is just 180 minus alpha, which is, oh God, goodness, what is that? Beta is equal to 180 minus alpha. I gotta calculate that. It's 180 minus 63.4. That's 116.6 degrees, which beta P2 is, in real life, divided by 2 is just beta divided by 2, which is 58.3 degrees. And that means that I would have to get to this face right here, I would have to go from the horizontal 58.3 degrees. And that 58.3 degrees over here to get to this point right here, if I start again from the horizontal right here, 58.3 degrees will be right here. This is 58.3 degrees. Look at 58.3 plus 31.7 is 90. Yay. Okay, so here, sigma 2 is at this face right here, my state of stress now, from at this face right here, representing 58.3 degrees, is negative 3.85, meaning compression, 3.85 KSI on the face here. And then equal and opposite, 3.85 KSI. Whoa, 3.85 KSI right here. Okay, and this is my principal stress state. There are no shear stresses in my principal stress state, but this is it. This is my principal stress state. So this would be my answer to part A of this problem, or part 1. Okay, notice I could have gone from sigma 1 here and just said, okay, well, if I go 180 degrees in Mohr circle, I go to sigma 2. So if I use sigma 1 as a reference, or I use this line as a reference, and if I go 180 in Mohr circle counterclockwise, then it's like going 90 right here. Okay, and that would have gotten me to sigma 2 as well. All right, anyway, that's just some food for thought. All right, I will come back in the next video and do the maximum in plane shear stress. All right.